Then welcome everyone to this talk. As introduced, I'm Philipp Terhörst from Paderborn University now. There I have a research group for responsible AI for biometrics. And in this talk, I will talk about how we can avoid errors that come at high costs. And at the last part, we will see how the utility of single pixels will contribute to this goal, which goes in the direction of explainable face recognition. And I want to start this presentation with some kind of bold claim, something that says, okay, current biometric systems belong to the most accurate machine learning models that we currently have. How do I come to this claim? If you look at the National Institute for Standards and Technologies, they have several nice experiments, experimental setups there, like the face recognition vendor test and so on, where a lot of companies or academic institutes can submit their works, and they evaluate it in a very big experimental setting. And if you take a look at these results and look at the top performing ones, for example, we see, for example, for verification, so one-to-one comparison, that if we set a threshold for a false acceptance rate of 0.001%, which is already very, very low, then for fingerprint as well as iris and face, the best performing industrial solutions have a true acceptance rate over 99.4% in these cases. So what I want to say is current biometric systems are pretty accurate, but they still do errors, especially if we move from these more or less constrained environments up to unconstrained environments. And even for the future, I think they will never stop making these kinds of errors, which is totally fine, depending on the application. For example, for unlocking smartphones, it's okay if I have to press my fingerprint on the sensor a second time on every, I don't know, 500 tries or so. That's totally fine. But if it goes to forensic investigations, or if you go in front of court, or financial transactions where also biometric systems are used, these errors can come at high costs. So, for example, in forensic investigations, you could send the wrong person to jail or search for the wrong person here. The same goes for in front of court. And if you think of financial transactions, if you use your fingerprint and let's say someone else can just use your biometric data to do these transactions, these high costs, these errors arise from are quite literally there. So we also have to consider that not only face recognition systems, but biometric systems in general have a growing effect of our daily lives. There are more and more applications and also many more that involves these kind of critical decision-making processes, where an error has a huge impact on individual persons, or if these errors consist more permanently even on society itself. So what should be the goal for, let's say, for the next years or so, that actions that are based on these kind of wrong decisions should be avoided. So the question is, how can we avoid wrong decisions? And if you ask my students, they will tell you we need more accurate models. But due to the nature of machine learning models, that they need data in order to learn, I think getting perfect models is in most cases not even possible there, just due to the complexity of the data needed, the model, the training process, and so on. What else can we do? For example, what we can do, we can try to reject uncertain inputs, which goes in the direction of biometric sample quality assessment, which just says, okay, try to prevent this garbage in, garbage out principle. If we have a face image that will produce an error with a high probability, just reject this before the sample will come into the system and ask for a better, for higher quality sample, in order to avoid these wrong decisions or minimize the probability for faults there. Or what we else could do, and this goes into the direction of the talk that we saw before, we can try to reject uncertain outputs, which goes in the direction of confidence estimation. So the idea is we can trust the decision only if the model is confident about its decision. So we ask them about the model's intuition, if the model is certain about the decision or is less certain about the decision. And if it's less certain about a decision, we can ask another model or human operator in these cases. Or in the last case, we can try to understand the model's reasoning. So the first, the upper two points go in the direction of how can we avoid wrong decisions in an automatic manner. And here we will include the human by trying to understand the reasoning, which is the term explainability. So if the reasoning does not make sense for the human, the user can decide not to trust the system, and therefore we can avoid actions based on wrong decisions, for example. And in the following, we will take a closer look at these 3 points and move forward in order to answer how can we avoid these kind of wrong decisions. And the first point that I want to go a little bit closer, because we'll need it in the last part for describing the utility of single pixels for explainable face recognition, is biometric sample quality. And this is defined by estimating the utility of a sample for recognition. So if you have a face image, for example, that is fully visible, then this has usually a higher utility and therefore a higher quality than a face image that is partially covered with a face mask or with hair and so on. So this has lower utility in this case. And the idea is that samples with lower sample quality have a higher chance of producing errors. And the idea is by rejecting these low quality samples, we can minimize the probability of making a wrong matching decision prior to any matching. And there are several factors that can affect the biometric sample quality, like different image characteristics like illumination, blurriness, resolution, or different factors of the face, even head posters, if you wear masks or make some crazy faces, or we even should include the model bias itself. And this is called face image quality if we compute the biometric sample quality with face images. I will go a little bit into details into one approach, just because we need it later, which is the stochastic embedding robustness approach, which is a concept of measuring face image quality using the robustness of a representation as the quality indicator. And if I say robustness, I mean robustness against dropout variations in this case. So the idea is if you have a face recognition model N, you can compute a lot of subnetworks M by randomly eliminating nodes, for example, with dropout. And each time you put a face image into this network, for example, you get a stochastic embedding out. And since we have small variations of these networks, these stochastic embeddings will vary a little bit. And if the network can deal well with the image, then these kind of embeddings will be very similar, which means we have a high quality. And if the network cannot deal well with it, these stochastic embeddings will differ a lot. So we have large variations in the stochastic embeddings, which refers to low quality. So why does it work? Because face recognition training aims at being robust against intra-identity variations, and an image that produces relatively stable identity-related embeddings despite these variations is an image with high utilization in recognition tasks. So straightforward from the definition of face image quality. So how does it work? Just to show you a little bit in detail. So we have an input image, we give it to a face recognition model that might consist of several convolution layers, pooling layers, and at the end we have a fully connected layer and the face embedding that it's the output. And what we're doing, we take the image, propagate it through the network till we have the second last layer, and here we randomly eliminate nodes and compute the resulting face template, which is X1 in this case, and this we will repeat by randomly eliminating nodes in the second last layer again to get this one. And we do it, let's say, 100 times. And then we compute all the pairwise distances between all stochastic embeddings. And this will allow us to compute the quality, which can be done with this formula here. And the inner part are the stochastic embeddings, stochastic variations, which is simply the mean pairwise distance between these stochastic embeddings here. So if we have a high quality image that the network can deal well with, here we have very low variations close to 0, which means if we put it here in the 2 times sigmoid function, this will be close to 1 in this case and refers to a high robustness to a high quality. And of course, the other way around, if the image has low quality, then we have a lot of variations here, which leads to a very low robustness and therefore low quality. So that's the basic idea. And if we think back of the idea, we want to avoid wrong decisions, want to avoid errors. This is basically what these error of reject versus reject curves show. So here we take the database, and for example here, for 20% ratio of unconsidered images, we labeled the database with image qualities, and then reject 20% of the lowest quality samples. And we can exactly see what we want to achieve. We can reduce the error from 0.6 to below 0.3 by rejecting low quality images. So we can avoid errors by avoiding these garbage and uncertain inputs here. And this works quite well. So that's one way how we can avoid errors. The second way how we can avoid errors is by rejecting uncertain outputs, which goes in the direction what we saw in the last presentation, confidence estimation. So if you ask a human to make a decision giving this face image and this face image, the human can make a decision, of course, but also the human can intuitively state how sure they are about the decision. And this is what current biometric systems generally can't do that well. But this is important because if they can tell you how sure they are about a decision, you can carry out justifiable actions based on this decision. So if the person is not sure, you will not take drastic actions based off this decision. And here we have to make some distinguish between score uncertainty and decision confidence. So if you make a decision and try to match these two, the decision might be a match. And the score uncertainty describes the uncertainty of the score depending on the certainty of the data in the model. So here we have a score of 0.42 plus minus 0.1, which is the score uncertainty. So the true comparison score lies within the range here. While the decision confidence refers to the decision made, so the confidence that the decision made is correct. And in this case, for example, this refers to a 62% decision confidence that the decision made is correct, which is the other part of rejecting uncertain inputs, avoiding these kind of errors. So if we have a low confident decision, it's more likely to be wrong than a high confident decision. And if we have a low confidence detected, then we can ask a more confident system, for example, or a human operator to make the final decision. So the question is, how can we get accurate and interpretable confidence estimates? And one way to do so is to compute a probabilistic interpretable comparison score. So the idea is we want to use the probability that a comparison score or even a set of comparison scores by comparing one sample with a lot of different samples for another person and compute the probability that this score or set of scores originates from the genuine distribution. And we can use this as a new comparison score and therefore also at the decision confidence for a genuine distribution decision. So the idea is if we have a score, for example, here 0.75, we can compute the probability that this belongs to was sampled from the imposter distribution rather than the genuine distribution, or the other way around, that this belongs to the genuine distribution rather than the imposter distribution. And you see, yeah, it looks like here, depending on the underlying data. So here you have your imposter distribution, the genuine distribution, and the probability that the score S here belongs to the genuine distribution just arises here similar to a sigmoid function, not exactly like one, because this depends on the data, and it's only sigmoid shaped if the overlapping area is symmetrical. So how can we compute this one? So let's say we have a sample and compare it to against n samples of a different identity. This gives us n comparison scores, or the set of comparison scores. And what we want to do is compute the probability that these scores, given these scores, this was generated or drawn from the genuine distribution rather than the imposter distribution. How can we do this? We can do this with Bayes' theorem. So this probability can be divided then into the probability that given the genuine distribution, we can draw these kind of scores times the probability that we choose the genuine distribution divided by the same plus similar with the imposter distribution. So the probability that these scores were drawn from the imposter distribution times the probability that we have an imposter sample here. So these are the prior probabilities that the scores belong to the imposter distributions. And assuming that these scores are drawn independently, these likelihood functions here and here can be calculated based on the probability that the score S has from the genuine times the probability of this, the genuine probability of score S2, and so on, and the same for the imposter. So these G outputs of the G of S is simply this kind of probability that we have for this kind of scoring. We can also simplify that. So for example, we can assume that genuine imposter comparisons happen, for example, equally often, which simplifies this to a multi-instance solution. Like we only have the likelihood of the scores belonging to genuine divided by L of G plus L of F, so that it belongs to imposter. And if we have a single instance scenario, so instead of having a set of scores, we only have one score, then this simplifies to G of S divided by G of S plus F of S. So the probability that the score was drawn from genuine, this score is produced by genuine divided by the same for genuine plus imposter. So if we want to get a confidence, then this score gives you the confidence, so the probability that the score was drawn from the imposter distribution rather than the genuine distribution rather than the imposter distribution. So the confidence for an imposter decision is simply 1 minus this kind of score. Okay, so far we assume that we have the genuine or imposter probabilities already given here. How can we get them? We can simply do this by probability density estimation, for example, with kernel density estimation. So we have a very simple and intuitive way of computing these probability densities and therefore computing this confidence estimations. But doing it in this way, this gives us a lot of properties that are very nice for biometric systems. For example, we have interpretable scores. So we don't only have a score that which means higher is better, more confident, and lower is less confident. By doing in this way, we get a probability which allows us to interpret it in a probabilistic way. So it reflects a probability that the comparison score really belongs to a genuine comparison, for example. And that makes it very convenient for many applications where we have this high risk decisions made where the errors come at high costs. Then we also have, this also has a high universality. So it works on score level only. So it's not limited to any biometric modality. it's not limited to any special kind of recognition models or so. And yeah, it's not even changing the single biometric performance here. But in contrast to this simple comparison score approaches, these kind of scores can naturally compute it when we have multiple samples given. So if we have one sample, let's say a person that we're searching for, and we have a video frame, so we have a lot of images from the same person, we can compare this one reference image with all the frames, get comparison score, and compute a joint comparison score that allows us to state the confidence and has the multi-biometric character inside here. And of course, it can be integrated quite easily into existing systems, just put it on top of an existing system without even retraining. And you don't even need to find the optimal threshold for your search false match rate, for example, with very data and computational expensive experiments. Because if you want to have a false match rate of, I don't know, 0.99, 0.0001, for example, you just set the threshold to 1 minus the false match rate that you want to have, because it's already aligned that the comparison score reflects the probability for a false match. In this case, for a true match. So let's take a short look how it works. For example, here you see the expected calibration error. So this is simply the weighted true probability minus the predicted probability. And you see that the approach works quite well and is quite close to the true confidence probabilities here. And if we move on to compute this kind of confidence not only with one sample pair, but with a lot of sample pairs. So we compare one sample against one reference sample, or against 2 or against 5 reference samples. What you can see is that the performance in general does not improve, but also the confidence. So not only face verification performance improves, but also the confidence of the model improves and become more accurate. So this is the second part of how we can avoid these kind of errors that come at high cost. And the last one is to try to include the human here. So we want to understand the model's reasoning to avoid high cost errors. And especially if humans, which means it could be experts, it could be non-experts, are able to verify, interpret, understand the reasoning behind the systems and how particular decisions are made, then we can we can really avoid these kind of errors. And this goes in the direction of explainable face recognition if we go to face biometrics, which more or less defines the task of make the face recognition process understandable for the human target audience. I emphasize this a little bit more. You will see later why, because I think this kind of point of choosing the audience is quite important here. But generally, this is quite hard to achieve because most biometric models lack transparency. Many are based on deep learning models. So we have some kind of black boxes where the internal logic and the inner workings are hidden. Then we also have the presence of multiple possible attacks like presentation attacks, morphing attacks, serial attacks that not only affect the model, but also must be reflected in the reasoning of the model that we want to achieve. Then we have leakage of privacy sensitive information that is quite important. Like we have explanations that might, for example, reveal information of the users that the users don't want to share, like health information and so on. And we have the presence of bias and unfairness in the models. So the model bias might also affect these kind of explanations. And then also the kind of explanations and explanation methods can be quite different. Right now, we have a lot of local explanations, where we try to have a single sample and look how the models reasons with this kind of sample. But I think the future will also go in the direction of global explanations. So try to explain the overall behavior of the model so that the humans can understand it. We have different data types, like a lot of images is currently used in biometrics, but perhaps it will also go into the area of text author verification and so on, especially if ChatGPT and so is skyrocketing right now. We have different purposes of interpretability. Currently, we have a lot of black box models that we want to understand. But what about creating models that are intrinsically interpretable and therefore don't have these approximated explanations here? We can use these explanations to make the model fairer, to avoid systematic errors here. And lastly, we have different kind of models that can be specific to a single model or group of models, or methods that can be applied to any model at all. And also these kind of explanations can help in many different places in the verification process, for example. So if we think here of the face verification process, where we have an input phase, usually first we give it to a pre-processing model where the face is detected, where we make sure that there's no presentation attack, for example, and where we ensure that the face image quality is high enough. Then usually we give it in a face recognition system, or today more deep network here, to extract the face template. So where the identity information of the person is encoded. Then during verification, we search for the name, like here it's Philipp. We search in the database for the template that is associated with the name Philipp, compare these two templates, get a similarity function. If this is above or below a certain threshold, we come to the decision that's genuine or imposter, it's the same person or not. And depending on all the different modules here, we can ask several questions that help us to understand the model better, that helps to avoid errors, for example. One is, why does the system think this image provided is an attack or not? If it's an attack, we might want to start making investigations, for example, and take some actions in real life. So we should be sure that's really an attack going on here. Or why does the system think that the image has a low or high quality? So especially if it's a low quality image, I will go into details at this point much later. Then the user might want to get feedback what to do in order to get the image accepted, for example, to get access to the airport area and catch the airport, for example. If we go to the extraction module, we could ask the question, what do individual features refer to? Can we already see which parts of the face are covered and explained here? Or if we go to the matching module, which parts of the face contribute to similarity, to dissimilarity, what we saw before in the presentations, and how does the system come to a certain decision at the end? Can we make this interpretable for the humans? And in the following, I want to just go through all these step by step, explain you some ideas, just to give you an overview before going into one of these topics a little bit deeper. And first is by explaining presentation tags. So here the goal is to understand if the image is really a presentation attack or not. And for example, what was done here, the feedback that was given to the human was based on a language, so not on some kind of saliency map or some similarity, dissimilarity in the face, but here they combined it with a language model, so that if you have some kind of attack, the feedback to the human is, this is a shiny plastic mass with green eye shadows, so the human knows what to look for to come to the same conclusion or just to verify this conclusion. And the same goes for this one here. Of course, this can be wrong, but this is one way to give giving explanations for example, presentation tags. Another one that we saw last year on this workshop was based on Webcam. So it was still the same goal to understand if the image is really a presentation attack or not. And what was more special here was that it should not be only the case, but also, especially for these kind of presentation attacks, the background might provide valuable information to make the decision. So it might be helpful if we detect, for example, the finger of the hand that is showing the photo inside of the camera. Then we can try to understand the face templates more. So in this case, the goal was that each face dimension, each face feature should represent a specific part or concept of the face. So here what was done was they initialized two different losses, a spatial activation diversity loss for the filters, so that the filters can learn to only activate locally. So you can see it here on the right. They show different filters and their responses, and the filters only activate very specific points in the image and not across all these things, so that we really have some parts that we can understand, like this area, and not some pixels distributed across the image. And then with the next loss, the feature activation diversity loss, they propagated this kind of information through the network by aligning the filter responses across all the faces and encouraging the filters to capturing more discriminate visual cues for the recognition, so that at the end, each feature represents a whole concept of the face. So if we match the templates, we can match these kind of concepts and understand these kind of concepts. And of course, at the end, if we have matching decisions, we can try to make this decision explainable for the human with, for example, showing similar or dissimilar parts of the face. And here the idea was, if we take a triplet of a reference, a mate, so these are from the same person, and the last one from a non-mate, so these are from a different person. We highlight the regions, for example, for the probe, that is most similar to the mate and least similar or most non-similar to the non-mate. And this was done by calculating the triplet loss and propagated back through the network. And the authors here also introduced some tree search. So in each step, they just looked at the K most activated nodes and only back propagated these kind of activations to get a little bit more discriminate features here. And you see the kind of outputs here for these images. They say, look at the left eye because it's most similar to this one and is similar to this one. Okay, here for this other image, it says, look to the nose and so on. So unfortunately, it's not symmetric here. But yeah, at least it gives some hints where to look for. Then we can also achieve this kind of explanations through perpetations. So here the goal was to find the parts of the face that are most relevant for the matching decision. And the idea was, if we compute two images, enrolled image here, probe image here, and compare it, we get some comparison score. And the idea is now we make some modifications to the probe image. For example, we systematically cover parts of the face. And if we cover an important part of the face and compare it with the enrolled image, the score will drop pretty heavily. And by combining this information of which part of the face is covered with how big is the drop, we can get some saliency map that shows you this part of the region was of the image was important for the decision, and this part was not very important for the decision. For example, here with you only see from Angela Merkel the right eye, and by comparing this image with this one, it focuses more on the right eye and less on the hand, for example. Which brings us now to the last bigger part here, which is the utility of single pixels for explainable face recognition. So now we are in the stage of we have an image and we want to understand which parts of the face are important for the specific face recognition model, and also give some feedback here. So if we have this kind of face image, we want to get this kind of pixel level quality maps, where red indicates this has a low pixel quality, a low utility here, and green indicates this has a high pixel quality. So we want to determine the utility of single pixels in this image for recognition with the specific face recognition systems. So why do we want to do this? Because we want to explain why an image can or cannot be used as a reference image for recognition. Also, if you think of you're going to the airport and you're standing at this automated border control scenarios, you're presenting your face and the system says no, image rejected. Many users will be like, okay, what should I do now? And here this kind of feedback can help to provide guidance on the reasons behind low quality images and provides interpretable instructions to improve it. Like this part of the face, please make changes in order to get your image accepted here. For example, here, the head is shown as black, so it might be shown here, please remove the head or make changes in this part of the face. And lastly, we can use it to better understand face recognition systems by understanding, okay, which kind of variations, environments, and so provide high utility, which parts of the face provide high and less utility for different face recognition scenarios. So how does the method work? If we take a face image, we give it to a face recognition model and propagate it through. And in the first step, we estimate model-specific quality values, which is the face image quality assessment approach that I showed you just at the beginning. So we just propagate the image to the second last layer, and here we repeatedly remove, randomly remove nodes and compute stochastic embeddings, compute the quality based on this variations between the stochastic face embeddings to get a quality value that we are also normalizing. Then in the second step, we build in an image-specific quality regression model. So what we are doing is we take the face recognition model and add a node at the end. So we connect this node with the embedding layer, and the weights here connecting these two layers are chosen such that if we give this image inside of the model, the output of the model will be our quality. So this quality regression model will only work well for this specific image here. But we need to do it in order to backpropagate now quality-based gradients through the network. So we can simply backpropagate them here and aggregate this information, which we get here, which is some kind of saliency map. And based on this information, we can aggregate this, normalize it to get a pixel level quality map, which provides us with the feedback that we want to have. So let's analyze it. And first I want to analyze it with pixel level quality change by enhancing the face image quality. So what we are doing is we take the original face image here, compute the pixel level quality map, and then these two images are given to a human observer with the task of please find and mask the quality decreasing factor. In this case, the human observer said, okay, here's a red area, so it might be the microphone here. I will mask the microphone. And this mask image is now given to an embedding model, and the quality decreasing factor, or potentially quality decreasing factor, is removed. And now if the face image quality from here to here improves, then we can say, okay, this was really a quality decreasing factor. So let's take a look how it works. First, take a look how it works qualitatively. So here you see a cheek that is covered, which can be seen in the pixel level quality map. Also, the image quality is 0.78. And the observer saw, okay, it might be the covered cheek here. And in painting, the cheek was recovered. And at the same time, the image quality increased. So this was really the quality decreasing factor. The same goes for here, where we have some kind of glass in front of the mouth with a low quality. It's clearly visible for the human, and even if the Inpainting was not perfect in this case. Still, the quality improved dramatically. So this was really the quality decreasing factor. The same you can see here for the glasses, which improves for the microphone, which is clearly visible and improves the quality, or even for multiple occlusions, like here the head and the beard that was removed with the inpainting, and the quality increases. So these were really the points here. Just in these cases that sometimes happens, the quality decreasing factor was potentially the glasses, but the inpainting failed. So the quality dropped because a face without eyes has not a high utility. And if we take a look at this quantitatively, we can see that in painting these low quality areas, according to the human observers, improve the face image quality in 65% of the cases. And in 15% of the cases, the quality decreased, which if we take a closer look at it, this was mainly due to these kind of inpainting errors that accidentally happens in some cases. So we can argue from that the pixel quality values are meaningful for humans, at least for the human observers in the experiments here. Then we can do it the other way around to analyze it. So we want to analyze the pixel level quality change by decreasing the face image quality. So we start with a face image like this, and then randomly add, for example, here, this kind of mask in different colors from 10 by 10 up by 50 to 50 pixels. And if we take a look at the qualitative analysis, we can clearly see these kind of disturbances in the quality maps. Also, if we take a look at the image quality change, so this is similarly the original image quality minus the mask image quality, we see that these kind of mask sizes start impacting the image quality itself. So the small parts here that are still detectable don't have a very strong impact on the face image quality itself. But if we take a look at the pixel quality change, which is the pixel difference in, or the average pixel difference in the area of the mask. So for example, we compare these images, pixels here with these pixel qualities here. Then we can see that they're all on the positive side. So generally, all disturbances lead to degraded pixel level quality values. So they are quite successful in detecting these low quality areas. And lastly, we can take a look at ICAO incompliant images. So ICAO refers to the International Civil Aviation Organization, and they announced some specifications that you have to follow. For example, if you go with your passport, if you want to get a passport, then you have to deliver an image that follows these kind of specifications, which basically says don't wear headgear, don't wear glasses, don't wear masks, have a frontal head pose, a neutral face, and a uniformly and well illuminated face. And here you see a lot of different incompliances with this ICAO specifications. And we can see these responses from the PIQ maps. For example, for the headgear, we can clearly see that this leads to very low pixel quality values. So they don't provide utility for the recognition task with the models that we used in the experiment. So this goes exactly with the ICAO specifications. The same goes for the glasses, but interestingly, it's more about the border of the glasses. So even if humans cannot see well that these glasses are a little bit transparent, the models can still see the difference and looks like they have a high utility still for the recognition task. Then for the mask, we can see they cover parts of the face, they don't belong to the identity, and therefore they have low quality areas. For the head poses, also becoming pretty interesting. If you look at different head poses, so I just showed you here 2 of them, I can show you more of these kind of results later on, if you're interested. It looks like that the high quality pixels are always the front part of the face. So even if you have a total profile image, the part that has high utility is the one that can be seen from the front. So probably this goes back to how the face recognition systems are trained based on the training data that shows very less profile images here. And also grimaces are pretty interesting. So for example, if you do a crazy face like this, where all, more or less all parts of the face are more or less disturbed, except for the nose, which is unchanged, this leads to a lot of low quality areas, except for the nose that is still has high utility, high quality there. Probably because these kind of images cannot be found in the training data so often. It's often neutral faces or smiling faces if you think of celebrities. So these kind of grimaces or disturbed parts of the face lead to low quality areas. And also pretty interesting illuminations. It turns out, so we checked it with multiple images, always the dark side of the face has a much higher utility for the recognition here. So this not only with these two, but for much more, and also for different face recognition models that we tested. It always turns out that the darker side of the face provides higher utility for the recognition network, probably due to these kind of reflections on the brighter side here that might confuse the model. That would be my guess. So with this, I come to an end. So we saw that errors in biometric systems can come at high costs. They can be avoided by especially the actions that can come at high cost afterwards for the society, for the individuals, can be avoided. For example, through automated rejection of the samples. So we talked about biometric sample quality, about confidence estimation, but also they can be avoided by explaining the model's reasoning to a human audience here. So explanations can be helpful at different places in the recognition process. We saw it for quality estimation in the last part, attack detection for matching decisions, and so on. And especially, we went a little bit deeper into the utility of single pixels for recognition, which can be helpful for explaining the reasons behind the rejection of low quality images, behind the low quality factors in these kind of images. And also it helps us to understand what is really important for an automated face recognition system that we cannot really look into there. And lastly, last slide, I promise. I want to give you some future challenges or recommendations, what I think might be important for developing this area further. And the first one goes in the direction was what Aaron Ross said in the first keynote talk. I think we should develop explanations. He said for the right applications, I say for the right audience. Why? Because if you have different applications, there are different audiences behind it. And they might have completely different prior knowledge. So if you think of end users and developers, they have different kind of knowledge that they were trained on, that they have, and therefore they need to understand these kind of explanations. That can be more complex for developers because they are into the thing, but the end users are just normal people and need completely different kind of explanations. And the same goes for the operators. So perhaps the future should go into making these kind of feedbacks specialized for different audiences. Then we should go in the direction of develop comparable evaluation protocols. There are many, many properties for explanations like fidelity, stability, comprehensibility, selectivity, and so on. They involve humans, which are not standardized. So we need some kind of standardized ways to evaluate and compare different approaches. Showing just qualitative results work now for many publications, but they are very hard to compare. So we need some way to make them really comparable, best way in single number values that we can really say this one is better than this one in this approach, just to not run very far in all directions at the same time, but make really steps in the right direction that helps us all. And lastly, if we think of very critical decision-making processes like in forensics or in front of court and so, I think there the direction should go into developing intrinsically interpretable models. So right now, the majority of the works in explainable biometrics go in the direction of approximating explanations, but this is not how the models really come to their explanations. They are just approximations. So it might be a nice way to visualize it, for example, but it's not really the truth how they make the decision. And this might be very dangerous if we too much rely on this kind of explanations for very high-risk applications where we need precise explanations, how the model really come to this conclusion. So with this, thank you very much for your attention, and I hope you have some questions.